Hello everybody, getting ready to do lesson 6.5 part 1 of classwork of pre-calculus math today. In today's lesson, you got 12 points here. It goes in your notebook, part 1, 6.5. And then we got 38 points here that will go into your classwork sheet. Today we have no bell work, but we go right into your notebook. The complex plane. Just as real numbers can be represented points on the real number line, you can represent a complex number, z equals a plus bi, as a point AB in a coordinate plane, the complex plane. The horizontal axis is called the real axis, so your horizontal is real, and the vertical axis is called the imaginary axis as shown. So this is your real axis, and then this is your imaginary here. The absolute value of a complex number, a plus bi, is defined as the distance between the origin 0, 0 and the point AB. So this would be an example here of the absolute value of a complex number, would be that distance there. The definition of the absolute value of a complex number. So the absolute value of the complex number z equals a plus bi is given by the absolute value of a plus bi equals radical a squared plus b squared. When a complex number a plus bi is a real number, that is, when b equals 0, this definition agrees with that given for the absolute value of a real number, a plus 0i equals a squared plus 0 squared. So when you have a situation like this, when b equals 0, you square your a, and then you take the square root of it. So which would equal a. In this case here, we have a situation that here, which equals absolute value of a. So let's try one. So going into an example here, find the absolute value of a complex number. So plot z equals negative 2 plus 5i, and find its absolute value. So the complex number in this situation here, z equals negative 2 plus 5i, and find its absolute value. So equals 5i is plotted. The absolute value of z would be negative 2 squared plus 5 squared, and you get radical 29 for the absolute value of this complex number there. Okay, so let's try one for number 11 here. Plot the complex number and find its absolute value. So we have up here negative 4 plus 4i, and we put that underneath a radical. Negative 4 squared plus 4 squared, radical of that. And we get radical 32, which becomes 4 times square root of 2. And then the plot for that would be like that. And then for number 12, negative 5 minus 12i. And when we square that and add them together and then take the radical, we get radical 169, which is 13. And then here would be your graph of that as well. Okay, notebook entry. Trigonometric form of a complex number. In section 2.4, remember, way back when, you learned how to add, subtract, and multiply and divide complex numbers. To work effectively with powers and roots of complex numbers, it is helpful to write complex numbers in trigonometric form. So consider the non-zero complex number a plus bi by letting theta be the angle from the positive real axis. So here's our theta here. This is our positive real axis here, so here's theta. So when we have this situation. Okay, so moving on here to page 6 of notebook. Measured from clockwise here, so here's theta measured from clockwise, or counterclockwise actually, that's counterclockwise, to the line segment connecting the origin to the point AB would be that line R. And so you can write A equals R cosine theta, So our A would equal R cosine theta, and B would equal R sine theta. So B would be R sine theta, then A here would be R cosine theta, where R equals radical A squared plus B squared, radical A squared plus B squared. Consequently, you have A plus BI equals R cosine theta plus R sine theta I, from which you can obtain a trigonometric form of a complex number. Trigonometric form of a complex number. The trigonometric form of the complex number z equals A plus BI is given by z equals R multiplied by quantity cosine theta plus I sine theta, where A equals R cosine theta, B equals R sine theta, and R equals radical A squared plus B squared, and tan theta equals B over A. The number R is the modulus of Z, and theta is called the argument of Z. The trigonometric form of a complex number is also called the polar form because there are infinitely many choices for theta. The trigonometric form of a complex number is not unique. Normally, theta is restricted to the interval 0 less than or equal to theta less than 2 pi. Although, on occasion, it is convenient to use theta is less than 0. Okay, so let's go into our next example here. Example 2, writing a complex number in trigonometric form. Write the complex number z equals negative 2i. So, okay, so here's theta here. That would be our theta, angle theta. Here is negative 2i down here in trigonometric form. So how do we write this in trigonometric form? So the absolute value of z would be r equals negative 2i, absolute value negative 2i, would equal 0 squared plus negative 2 squared would equal radical 4 would equal 2. So that would be your absolute value there. With a equals 0, you cannot use tan theta. You can't use tan theta, b over a, to find theta because z equals negative 2i lies on the negative. Okay, so moving on to our next slide here, the imaginary axis. So choose theta equals 3 pi over 2. So this would be 3 pi over 2 down here. So the trigonometric form is z equals r times cosine theta plus I sine theta, and that is 2 times cosine 3 pi over 2 plus I sine 3 pi over 2. Let's try one now. Represent the complex number graphically and find the trigonometric form of the number. So we have 23 here is negative 8i, and then 24 would be 4i. So for this one, okay, so represent the complex number graphically and then find the trigonometric form of the number. So we have for 23 here we have negative 8i. So graphically it will be down here. This is negative 8i. And then to find the trigonometric form of the number, z would equal negative 8i. And then our r here would be 0 plus negative 8 squared radical would equal radical 64 would equal 8. We can't use tan, but for theta here we can use 3 pi over 2 to give us our theta there. So coming down here, z equals 8 times cosine 3 pi over 2 plus I sine 3 pi over 2. There is your trigonometric form of this number here. And then down here, 4i, this would be the plot for 4i. And then z equals 4i, r would equal 4. Tan, it would be 4 with 0 undefined. But theta in this case would be pi over 2. So we stick that out in front here, would be 4. Z equals 4 times cosine pi over 2 plus I sine pi over 2. So there is your page 10a. Moving along now to our next example, writing a complex number in trigonometric form. Write the complex number z equals -2 minus 2 times radical 3i in trigonometric form. The absolute value of z would be the absolute value of -2 minus 2 multiplied times radical 3i. And then this, we have our a and our b here. So our a would be -2 squared plus -2 times square root of 3 squared, and all underneath the radical. This comes out to 16, which will equal 4. And the angle is given by tan theta would be b over a. In this case, it would be -2 multiplied by radical 3 over -2. These cancel, you get radical 3 for tan. So because tan pi over 3 equals radical 3, and z equals -2 minus 2 times radical 3i lies in quadrant 3, choose theta to be theta equals r plus r. Theta equals pi plus pi over 3 equals 4 pi over 3, which is right there. So the trigonometric form is z equals r cosine theta plus I sine theta in this situation here. So that would be 4 times cosine 4 pi over 3 plus I sine 4 pi over 3. That would be the trigonometric form of this number up here, z. Okay, into an example here. Represent the complex number graphically and find the trigonometric form of the number. So here's radical 3 plus I. We need to first of all represent the complex number graphically. So for that, to graphically, we're going to hold off until we find the trigonometric form of the number. So z equals a radical 3 plus I. And then for r, we need to put everything underneath the radical here. Be the radical 3 squared plus 1 squared, which would equal radical 4 would equal 2. Tan theta would be would equal 1 over square root of 3 equals square root of 3 over 3, and that would equal 2 pi over 6. So z would equal 2 times cosine pi over 6 plus I sine pi over 6, and the graph of that would be right like that. Pi over 6, this would be your theta here. And then down here, -1 minus radical 3i, r would equal 1 plus 3 radical 1 plus 3 would equal 2. Tan theta would equal radical 3 over 1, which as theta would be 240 degrees, radical 3 over 1. So and that would be 4 pi over 3. So we're talking third quadrant for that. So now we have 2 times cosine 4 pi over 3 plus I sine 4 pi over 3. And then the graph of that would be like this. That would be -1 minus radical 3i would be right here. Okay, moving into our next example. Writing a complex number in standard form. Write the complex number in standard form, a plus bi. Here's our number here. Z equals radical 8, bracket, cosine negative pi over 3 plus I sine negative pi over 3. So, because cosine negative pi over 3 equals 1/2, and sine of pi over 3 equals negative radical 3 over 2, you can write z equals radical 8, bracket cosine negative pi over 3 plus I sine negative pi over 3. So when we do that, we have 2 times, this becomes 2 times radical 2, bracket 1/2 minus radical 3 over 2i. And then when we crank that through, we come out with radical 2 minus radical 6i. Okay, let's go into another guided practice here. In exercises 47 through 58. Represent the complex number graphically. Represent that graphically. And then find the standard form of the number. Same thing down here. So, actually, you know, I would rather, well, I can do the first one. So for 47, 2 cosine 120 degrees plus I sine 120 degrees. So we have 2 times 1/2. So we have negative 1/2. Cosine 120 is negative 1/2. Plus I sine 120 be radical 3 over 2. And then this comes out to be negative 1 plus, these cancel here, radical 3i. And then the graph of that would be right about there, would be your graph of that. And then down here, 5 cosine 135 degrees plus I sine 135. I'll let you do that on your own, and that is 6.5 part 1. Here's my email if you need solution PowerPoints, class worksheets, homework sheets, anything else. Thank you.